Sit on it.
Nothing there.
Sit on it. There's nothing
Nothing's
wrong
wrong
with
with
it
it.
except when after you sit on it.
Oh my God, you said it.
Why are you freaking me out, man? Why are you getting inside my head?
You're being recorded.
All right. I don't know if I should wait any longer.
You can slide off.
Just get going.
Yes,
Do we have
that's
any
the chair.
folks out in there?
Yeah,
TV land?
there's a couple people.
I know we have.
We got Greg. We have Bill now.
So just to caution everybody again, the rustling of tinfoil and paper is really annoying long distance. So if you can open your pen.
Yeah. Hopefully it won't be as much of a, I don't know. I don't know if I can move this any further away. All right. So I'm going to be talking about monads. Now monads have a reputation in the Haskell world of being incredibly difficult to understand. Well, really, they have a reputation of being incredibly difficult to learn, and then once you understand them, they're not that hard. Well, I'm just going to try and explain them. Obviously, if you have any questions, let me know. I will not pretend that I am magic and can explain them super easily. So I'm just going to actually hop right on in. I think right now, so far, we've kind of been taking the approach of this is what a functor is, or this is what an applicative is, and kind of explaining it from the top down. I'm going to try and construct it from the bottom up because I think for monads it's a little bit easier. So I'm not even going to talk about those things yet. So I'm just going to say I have these three functions, and these are safe versions of unsafe functions that are just built into Haskell, specifically head, tail, and division. So safe head and safe tail should be pretty obvious. Safe div can blow up in the event that you try and divide by 0. So these all handle all those cases, and they catch them. So what I want to then be able to do is I want to use these functions to write my own function, which I'm going to call divide numbers. And what I'm going to do is I'm going to take a list of integers, and I'm going to take the first two integers, and I'm going to divide them. Actually, we're not going to use integers. Let's use doubles. So that way we can have fractions. So we're going to take the first two numbers, we're going to divide them, but we want this all to be safe. So if anything fails, we want to return nothing. And I think that's a reasonable thing to want to do. So what we might want to do, what we would normally do to do this, is with the unsafe versions, we would just say, well, we're getting some numbers, and we are going to take the first one, and then we're going to divide it by the second one. And this is really obvious, but if we want to change this to the safe versions, this is obviously not going to work. Oops.
I think, yeah.
Oh, yeah, you're right.
Never mind.
Yep.
Safe.
So we'll just use parentheses.
Safe.
Yep, I can't spell. So anyway, so this obviously won't work, and the reason why is because all of these intermediary things return maybes. And that's really, really inconvenient. If I try and run this, everything's going to loudly blow up. So what we really want to be able to do is kind of get the value out of the maybe, pass it on, but only if it's a just. If it's a nothing, the whole thing should just return nothing. So this sounds like we've kind of been building up a bunch of tools to do this kind of thing. We've looked at monoids, which let you take two things that are wrapped in a context and combine them into one. We've looked at functors, which let you apply a function to something inside of a context. Applicatives let you apply a function in a context to things inside of a context. So it sounds like some of those things might be useful here. The trouble is that we actually can't really use any of them here. Try as you might, if you use like fmap and apply from applicative, you're not going to be able to get this to type check. And the reason why is if you look at the type signature of fmap, it takes a function from A to B, and it kind of lifts it into the context, right? So you have this pure function, and then you operate on maybes. But the trouble is that these functions that we have, they don't operate from A to B. They take a value that's not in a context, and they return a value that's in a context. And that inherently does not match up with this particular type signature. So what we really need is a different function. And what we need is a function that takes an A to a maybe B, and then takes a maybe A and returns a maybe B. And just to make how the argument order will work out and to make it a little prettier to read, I'm actually going to swap these around. This one's going to come second. And so I'm going to give this function a name. I'm going to call it and then, because we kind of have this idea of we're doing an operation that gives us a maybe. We have another operation that takes the value inside of that and produces a maybe B, and then we get back the maybe B. So this is really, really easy to implement, actually, if we just implement it ourselves. So I'm just going to take this type signature directly, actually, and so basically if we get a nothing, then it's really obvious what this is going to return. It's just going to return nothing. And if we get a just and a function, then we are going to apply f to x, right? So if I run this, this should all type check. Yep. So really straightforward what's going on here. And so now we can actually use that to implement our divide numbers function. And no, because keep in mind that this function returns a maybe. That's actually why this is how this differs from fmap.
Gotcha.
Is that if there were the just here, then it would just be fmap. But it's not. So yeah. So I'm going to comment this out, and I'm going to write this now using our and then function. So this is going to look a little bit weird, but basically what we're going to do is we're going to call safehead, and we're going to call and then. And I don't know if people have seen the sort of backticks in Haskell, but this lets you turn a function, just an ordinary function, into something that is an infix function. So you put it in between the two arguments instead of at the beginning. But that'll make the code look kind of pretty. So we can say we're going to run this, and then this basically, the reason I put this function last is it's basically going to be getting a callback, which takes the result of this operation if it succeeds. So I'm going to take this, and I'm going to get back the actual head. So I'm going to call that A. And then I'm going to do the same exact thing. I'm going to get the tail of this. And I'm going to call this rest. And then we're going to take the head of rest. So we're just kind of using and then each time to sequence these operations together. And we just give them a callback that take the result. So then this one's going to get B. And then finally, at the result of all this, we can now do safe div, and we can just divide A by B. And this will now actually type check. So this is a little bit confusing, but I don't think it's too bad. So everyone in this room, at least, kind of understand what's going on.
Could you highlight on the right side of the and then
Yep.
to the type signature of the and then to
Yeah. So like maybe it would be helpful to add some parentheses actually, to kind of see how the grouping works out. So basically the way this works is we run this operation and we call and then, and we give it this whole expression as kind of the callback, and it gets the value that was inside of the context. We're just giving it a name called A, and then we're going to keep going. And if any of these computations fail, it will just ignore the callback, and the whole stack will return nothing.
When you say callback, do you mean the second parameter of and then?
Yeah, that's just the function I'm passing in. In another language, like in JavaScript, you would probably call it a callback. In Java or in C, sometimes they call it a callback. But in Haskell, it's really just a function.
Okay. So
But yeah, it's just the second argument. So this might not look terribly pretty, but it does kind of mirror. One way that might be easier to visualize this is if we did it without our helper function. So if we said something like this, right? We did this just using nested case, and we did it like this. And then so here we did case. Let's line breaks. And so basically each and every time nothing happens, we just break out and return nothing overall. But otherwise we keep going. So this is like the exact same thing, but using nested cases. So you can see this kind of like unfortunate rightward drift we have going on here, where every single time we get a value out, we have to add another layer of indentation. And the same is kind of the problem with this one too. They do the same thing, and then it's just kind of like taking, because obviously this nothing to nothing is exactly the same in every single use case. So we can just pull that out and do our function right here is what this case does.
Just to add something.
Yep. And it short circuits effectively. Every time we get nothing, we don't even try to keep going. We just return nothing. But so this one's obviously a little bit nicer. So let's prove that it actually works. First, see what happens. So I'm going to pop open a little REPL and just open this up. Let's make this bigger. It just makes it so I have to manually load in my file here. So I'm going to load up source lecture maybe is this file here. So we have divide numbers, and that just takes double to maybe double. And I'm going to give it some numbers to divide. So I'm going to divide 13 and 6, some arbitrary numbers. And there we go. So we actually get back a value. But if, say, I try and divide 13 by 0, we get back nothing. If there's only one element, we get back nothing. If there's no elements, we get back nothing. Now, obviously, we don't actually check if there's more elements. So if I gave it 13, 6, and 7, then it'll just ignore the other elements. But you can see how that actually works. Now, we can actually make this a little bit prettier by just changing our indentation a little bit. And it'll actually work if we just align these all up. So you can kind of see how by using this kind of and then function and this little trick, we can get something that looks just kind of like a straightforward sequence. We basically say run this operation and store it. It's kind of like let, but reversed. The thing you bind it into is on the right-hand side. So we say run safe head, stored in A, run safe tail, stored in rest, and so on and so on. And so now we have a pretty nice sequence of operations. So this is good. This is obviously an improvement. But there's kind of an issue, which is that you may notice that when we run this in the REPL and we give it some value and we get back nothing, we have no idea what went wrong. Something went wrong in our stack of functions, and we don't know what it was. So what we want to do is probably have a nicer way of keeping track of the errors. And the traditional way to do that in Haskell is you go from a maybe to an either, because an either lets you basically tag each failure with a little string that says what went wrong. So instead of returning nothing, we're going to return left and give it an error message. So in the case of, this is like the exact same API as the maybe one, but I've just upgraded them all to ethers. So now you can see that they're all pretty nice. And theoretically, if we sequenced all these things together, we would just want it so that as soon as an error happens, as soon as we get a left, the whole operation would fail, and we would see that error message, just like the maybe situation, but with left instead of nothing. So the cool thing about this is that we can now actually implement and then for our either type as well. So it's just going to be a little bit different. It's going to say given an either of, and I'm going to use the first type variable is going to be e, because that represents the error, the left-hand side. And so now we have a function that takes an A and produces an either of EB. And then finally, the whole thing will return an either of EB. So you can see that the error type itself never changes. It's just always going to be a string, because all these errors are strings. But the actual value inside of the either changes as we sequence things. So this is going to look very similar to what we had before. We're basically just going to say, given a left of something, and it doesn't matter what the function is, we're just going to return it. And given a right of something and a function, we're going to just apply f to r, and now we have the exact same thing that we did, but using ethers. And the really cool thing about this is that now I can take this divide numbers function and I can legitimately just copy and paste it in here and change this to right or to either string double. So I'm just changing the type. I'm not changing the implementation at all. And this is going to type check. And that's because this and then function is pretty general. We've just defined it on a different type, and we're getting the exact same functionality. But now, when I pop open my REPL, and I run this again, so the reason I'm loading these individually is because there's functions with the same names. So if I loaded them all at once, it wouldn't work. But so That's why I'm going to load up either now. So again, we have our divide numbers function. So we're going to do the same exact thing. We're going to divide 13 and 6, and it works again, but now we're getting back right. So that's pretty cool. But if now we do something bad, like trying to divide by 0, we get an error message, and it just follows through the entire stack, and we get back a failure case. So we can also do the same thing if we don't pass in enough elements, or So there you go.
Somebody asked a question. Is that right?
Oh yeah, was that what? Was that? Nope.
Nope.
All right. So I think everyone can kind of see why this is a useful function to have, and not more importantly, but equally as importantly, why it's different from all the things that we've talked about thus far. It's not fmap, it's not apply. It's a little bit different. And so Haskell, just like having the functor type class and the applicative type class, has a type class called Monad, which has the and then function in it, except that Haskell calls it bind. And the reason for that is, you can kind of think of it as like the left-hand side gets bound onto the right-hand side. It also gives it a funny name. It's not actually spelled bind. It's spelled greater than equals. This is maybe not the greatest choice, but it does turn out, it does end up looking pretty nice. So instead of using our custom and then function, I'm just going to use bind here. So again, we don't need to use the backticks now because this is an operator, so it's automatically in fix. And I can run this and type checks. Now my linter is telling me to do something way too complicated for this lecture, so I will not take its advice. So now this is exactly the same thing, because the bind instance for either is actually the same thing I just showed you for and then. So I can actually run this again, and it will do exactly the same thing as it did before. So if you actually look up the implementation of Monad for either, you will see that this is what it looks like. Now, Monad is a type class, so let's actually get into the theory here a little bit more. So every monad is already a functor. So the syntax looks like this. We basically say a monad has to be a functor, and it has two. It has to be an applicative, and an applicative has to be a functor. Didn't used to be that way, but now it is. And it has actually, the first one that we've already talked about is bind. And so this is pretty simple. It's exactly like what it looks like up here. It's that we have a MA to A to MB to MB. And so you can kind of see, we need parentheses. You can kind of see how this resembles this type signature right here. It resembles this type signature right here. We're just swapping out maybe and either for the M. So there you go. There's actually another method of this type class called return. And this is also somewhat poorly named because it's often confusing, because return means a very specific thing in imperative programming languages. And it's a little cute because sometimes it kind of looks like return in imperative programming languages in Haskell, but that's actually not what it does. It's very simple. It takes an A and gives you back an MA. And you may notice, if you think back to applicatives, they have a function called pure, which looks exactly like this. And it's exactly the same. This is kind of a historical detail because monad was invented before applicative. It used to be that there was no applicative and there was just return and no pure. But now return and pure are always identical. So that's a little bit annoying. But the relevant bit is this bind right here, and it does exactly what I've demonstrated.
So do you not have to define return in your monad if it's already an applicative? It already has a pure. Would auto-define?
Only if you call it pure.
No,
It will.
I think it will. Yeah, there's a
Automatically give you
default implementation.
Yeah.
Yeah. So
Cool.
so let's
The class itself.
Yeah, that's what I mean.
yeah. So in fact, I kind of want to show off doing that. So I'm going to hide the either type from the standard library and implement it ourselves so that we can actually see what implementing this would look like. So basically, I'm going to create an instance of monad, and we're going to create an instance on either. And basically, so we just need to implement bind. And
I think you need to implement the data structure too.
oh, well, yeah, of course. Thank you. Like that. And so bind is going to look just like our and then function. So I'm just actually going to copy this, move it up here, and I'm going to replace these two things with bind. And if we wanted to, we could actually, well, no, that's fine. All right, so now we have, everything's on fire. Why do I not? Oh, yeah. And yeah, this has to be an instance of applicative and functor. So we have to define that ourselves really quick. So I'm just going to make this instance of functor, which is pretty straightforward. Fmap over left is fmap something over left is left. Fmap f over right is right of r. And then let's also implement applicative. So now you can see we're going to implement pure right here, and this one is going to be really simple. It's just going to be right, and we need to implement apply. So we're going to say, given a value, a function wrapped in a context, or given something wrapped in a context and a value, then we're going to apply it. And otherwise, if either of these two things are left, then we are going to.
I think it's.
Oh.
Yeah, I think it's.
Yeah, you need to do two cases for this, right? Because you need to do left. This would be easier if maybe I was doing it with maybe, but oh well. So if either of these things are left, we'll just return the error. Okay, so now we've implemented all the things we need to implement monad, and we get this type class now. So I'm actually going to pop open my REPL again, and I am going to load up this file. All right, so hopefully I should be able to, yeah, okay, it doesn't conflict. Okay, so now I should be able to demonstrate that return will actually work. So I can say, oops, that's not going to work because it doesn't know what kind of thing we're using. So let's say this is going to be an either string integer.
It doesn't have to show us.
Oh, thank you.
You derive that.
Thank you. Always gotta derive the basic things.
Well, when I do each in there, yeah.
Yep. All right, let's reload this. Do that again, and there we go. So you can see that it just uses the pure instance. And we can also just use our divide numbers just like before. So divide numbers, divide by 0, and it fails. So that's our home rolled monad instance. So they're not that complicated. Sometimes it's a little bit hard to see why this bind operation would be useful. But you can see that in these contexts where it's really just about sequencing things. It's about sequencing operations and pulling values out. So so this is the basics of what monads look like. And so you might lead you to believe that monads are all about, well, we have operations that can fail or that can short circuit in some way. But monads are actually way more general than that. So the reason for that is in another programming language, you might have something that is other programming languages, imperative programming languages, have things like monads, except that instead of looking like this, they call the bind operator semicolon. So what I mean by that is in another programming language, like JavaScript, you might have a function, and this function can do multiple things as well. It could say, do something, semicolon, do something else. So normally in another programming language, this semicolon doesn't do a whole lot. It just runs the first one, then runs the second one. But in Haskell, you can adjust kind of what happens in between the two expressions. So that's like super general, and you can do a million different things with that. And there's lots and lots and lots of different ways to use and abuse this functionality. But before we move on, I'm going to say that first of all, this syntax right here doesn't look as nice as that.
Just back on that analogy that you were doing with semicolon.
Yep.
Isn't it more like do something and if and then do something else?
Well,
is what the bind is serving the purpose for? Or?
Not quite. It really is just like it could be that. It could be. It's basically any arbitrary thing. It's kind of like you have these sequence of operations, and normally the semicolon just says, "Okay, we did this one. Do the next one." But
in fact, you have an example of that in your safe head. Between the first and second, it doesn't take the.
Well, I could here.
No, where you actually use the.
You can show the divide when you actually
The
pull the
div.
divide.
Yeah. See, between the first and the second, you didn't use it. You didn't use NS.
Well, here. This is actually a good idea. We can create JavaScripts semicolon or any other programming language semicolon with a very simple monad that happens to be called the identity monad. And this is the monad that doesn't do anything, and it's really easy. We can basically just say just to make this simple. So that's not a module, that's an instance. All right, so we'll just create a functor instance for identity. And so identity is really simple to implement everything for, because you basically just say like, we have a thing, and we don't do anything, we just apply f to x. We're just wrapping, this is the do nothing data type. So we can do the same thing for applicative. And so pure is, as usual, just our constructor. And we have apply. And now this is wrapped in identity. The exact same thing. We just pull this one out. Does nothing at all. So now we can get to the interesting part, monad. And this one's also going to be like the simplest possible monad you could ever write, which is we have bind, and we have a value in a context. And we have a function, and we're just going to do this. We're literally like, there's no logic here. We just take the value, we apply f to it. And so now you can see that like if we actually use this monad, then we can, basically what we're going to do is take some value and produce an identity value. And I'm going to derive show on this. And I'm just going to take a value, and we're just gonna let's make this an int so we can do something interesting with it. We're gonna add 1 to it. We're going to divide it by 2. So we just need to put our binds in between each one of these things. And so this is really simple. I can now run this. Oops. Yes, this needs to. Well, we can use return. So it's basically when we have this x, we want it to be an identity x. We can just wrap it up.
Because it has to be in the context.
Oh yeah, all these things need to. This is a bad example for. Basically, when you're using an identity monad, it's like there's no use for it because you just have to keep constantly wrapping. So let's just put returns everywhere. It's a little bit silly. And we can't divide. Let's divide doubles. There we go. Okay, so this is a really stupid function. But the reason I bring it up is because you can see how like this is the just like do a thing, then do another thing, then do another thing that you would see in most other programming languages.
Use the lambda instead of the return dot.
Yeah. Well, you know what? It's okay. I don't need to get too much into this because it's not super exciting. But like.
You haven't loaded it.
I haven't loaded it. You know, it just does those operations. And again, like you would never write this Because if you're literally doing nothing with all your monads, you would just say, you know, you just write, what was it? I wrote add 1 to it, so I would just write x plus 1 divided by 2. Like, that's what any sane person would do for this function. But you know, you can if you really want to get crazy. I almost feel like people often start with showing off the identity monad because they're like, it's the simplest possible monad, but it's so meaningless that you don't understand why it would be useful. So whatever. So anyway, getting back to what I was going to talk about, this syntax is obviously very flexible because we can swap out what bind means for all these different data types. But I think it objectively probably looks more confusing than JavaScript's like do a thing, do a thing, do a thing. And sometimes using this bind operator directly actually does look pretty nice, and it makes a lot of sense. But when you're just sequencing operations like this, giving them all names, then there's a special syntax that Haskell has only for monad, and it's a special type class that has like syntax support in the language, which is why it's so important in Haskell. Well, it kind of goes both ways, and that syntax is do.
I would suggest to keep that function there and then have another one.
Sure, have another one. That's a good idea. So let's do another one down here. I'm going to call this divide numbers prime. And this one's going to use do. So basically the way this works is that each bind, you transform it, so you kind of flip them around and you say, instead of having A and then you kind of like bind into A, you flip it around, you do this, and you basically just do that transformation a whole bunch. So this is now going to be safe head of, or safe tail. And then this is going to be safe head of rest. And then we're going to do safe div of A and B. Oh, you're right. Thank you. All right. So you can see that this looks a lot more like kind of an imperative style of programming, where you just say, do a thing, do a thing, do a thing. But underneath, it's doing the exact same thing that this is doing. It's just some nice syntactic sugar.
Yeah, Scala has lifted this as
four comprehensions.
Yeah.
Yes. So Scala calls bind flat map,
Right.
and they call do notation 4. But otherwise, it's almost exactly the same. But came here first. So now one thing that is possibly of note is that a lot of the time people will try and say, all right, well, safe div returns in either. And so they'll do stuff like this. So they'll say results. They'll do that, right? And they'll like just return that because they're like, well, we got to pull it out. You can kind of think of like when you do this, when you have this arrow, it's like pulling it out of the wrapper.
What is the return result?
Yeah, this won't type check. And the reason why is the last expression in a do block is legitimately like, it's a very dumb transformation. It just puts binds for every one of the arrows. And so now the trouble is that result here is needs to be an either string double, but we've pulled it out. So this result is just a double. And so you could do return to wrap it back up in the context. And like sometimes people will write code like this, where they'll like have a bunch of sequences and then they'll just return the result of something they've pulled out on the line before. And this is like people who who use the do notation but don't understand what it expands into, because this is like a totally pointless operation. This is a no-op.
Show the linter's complaining.
Yeah, the linter's yelling because it says redundant return. Why not? Not do that. And there you go. Now there's one other feature of do notation, which is that you can have, like, if I do something like, what's a good example? What's a way to do this? Let's say I wanted
value out. Stub value.
Well, I was saying, like, what if I wanted to do some other computation that doesn't return either? Like, maybe I wanted to say a plus 1 is a plus 1, right? So, and then I'm going to do this. This actually won't work, and it might be confusing as to why it won't work. It's going to fail to type check. And the reason why...
A plus 1 is not a...
Sure, it's not either.
Exactly. And And because bind only works on either's, and this arrow is just secretly a bind, this doesn't work.
Can we return there?
Hmm?
Return a plus 1?
That will type check.
So we could do a return, and that would work.
Yeah. Okay.
Oh, what's the
But-
linter say about that?
The lynch is probably yelling about that too. Yeah, so it's telling us to use let. So the thing is that normally when you want to have a pure computation inside of the sequence, if we want to do that up here, we would say, well, let a plus 1, it's a plus 1 in all of this stuff, right? And that would work. And we can do, there's the syntax of the do notation mirrors that. It's that we can say let a plus 1 equals this,
Okay.
and that will type check.
But you're not required to have the in the do.
Right, you're not required to have the in the do because it's you're not required to have the in keyword within a do block because there is inherently a sequencing of operations, which is normally not true in Haskell. Haskell differs from imperative programming languages in the significant way that there is no concept of like do this thing, then do something else. Everything is an expression that evaluates, and it kind of like evaluates to something else. It has a very nice reduction model. There are parts of Haskell that actually violate this, like seek. This doesn't. This is totally a valid standard reduction-based Haskell program because it just turns into this. It's just some pretty syntax that lets you get away with writing programs that are kind of imperative because functional programming is great, but there are some problems that are just best solved with like do something, then do another thing. But Haskell is powerful enough to be able to embed that style of programming into its functional programming. That's basically why monads were invented. Now, I do have some other stuff to talk about, but I think I'm going to, because we pushed everything back a week, we have this convenience of I can yell I can have a captive audience again next week, which is wonderful. So I'm actually going to hold that off for next week and just leave it at this. But I will say, just as a very quick closing comment, monads are the mechanism by which Haskell lets you have side effects like input, output, I/O, and embed it into its pure programming model. And the reason why is there's a magical monad called I/O. So if we wanted to have a very simple program that like reads something and prints it back out, and so we have this magical I/O monad, and we're basically going to say some input, read.
Get line.
Yeah, that's fine. What is it? It's
ln. Yeah, there you go.
put stir ln. Thank you. So I/O is this is a valid Haskell I/O bound program, but you can't. The reason monads are so important in this particular situation is because you'll notice that this is not actually doing anything. We get back a value of type I/O, and we can't ever run that value. Like so if I could even make something that just gets the value. So I could say maybe something that reads in a number and adds 1 to it. So we're going to read in a number, and we're going to return some input plus 1. And then this is going to be, what did I do wrong?
Map the read over the get line. The read is a.
Oh, right. Isn't there like a I/O one that reads it from I/O? Or am I just lying?
Yeah,
Read I/O.
Oh, what is it?
Oh, that I think actually,
Oh, so you still have to.
String it.
weird. Okay, well, whatever. So then let's do that. Let's do get line, and then let's use our let. Say int input equals read. Oh man, at this magnification, my tooltips are very inconvenient. And then we can use put here. Okay, so this is a very simple computation. You see it returns an IO int. And you can't, a lot of the times in Haskell people say, well, I want to get the int out of the IO int. And you can't, because this is effectively, the monad is just building up a instruction to perform these actions. It's like a recipe. And your entry point to your program has type IO unit. And that is the only way to ever run these IO actions. You give them to the very, very top level entry point of your program, and VHC, the compiler, will figure out how to run those instructions and actually execute them. So IO is a magical monad. You cannot find the implementation of IO in Haskell, but this often leads people to believe that monads are much more magical than they actually are, which is why I really only wanted to talk about maybe and either, because I think those demonstrate that this is not actually a complicated concept. It's just bind, and that's it. That's all it is. So there you go. That's it.
I didn't hear anything about burritos in there. I'm disappointed.
Is IO in the runtime?
Yeah. It has hooks into the runtime.
There was a noise a minute ago. Did somebody ask a question?
No one asked any questions.
Not ask any questions. Well, any questions?
So what's the burrito analogy?
All right, so I should probably so monads traditionally are really complicated to understand, and there's like a million tutorials on the internet.
Yeah, should I just look up the tutorial?
Well,
No,
the
absolute
joke,
goat.
yeah, there's like a billion different tutorials on here's what a monad is, but they're really bad. They're almost universally terrible. And so the burrito joke is that people will make analogies to just arbitrary things that they happen to find useful when understanding what a monad is, but are completely useless to every other human being on the planet. So burrito was one used in a particularly well-known blog post, and ever since then there's the joke that monads are like burritos. But that's a pretty useless analogy.
The burrito was tongue-in-cheek originally.
Yeah. But yes, that's the joke. And there was a paper written called "Burritos for the Hungry Mathematician," which explains burritos in terms of monads as a joke. So if you're nerdy enough to understand that brand of dry humor, you can look it up, and it's kind of amusing. That's it. All right. Yeah. Homework?
You want to turn the recorder on? Or
Yeah, I
should we
can-
Should we keep it for the homework?
Laser, do you want me to stop recording?